If I told you that Python just completely annihilated Rust in a rigorous, like, CTU melting mathematical benchmark, I mean,
Yeah.
beating it by over 300%, you would probably tell me my timer was just completely broken.
Oh, yeah. I mean, it sounds like a typo in a spreadsheet, right?
Yeah.
Python is beloved, obviously, but nobody really expects it to win a pure drag race against, systems level languages.
Right, but it's actually real.
Yeah.
So welcome to this deep dive where we're tearing down this highly specific, incredibly intense performance showdown. And I want you to imagine just for a second that you have a stack of paperwork a mile high.
Okay, a mile high.
Yeah, a massive stack. And you hand it to three workers. You've got a veteran accountant, and they represent C++ knows. Then you have an ultra-cautious auditor representing Rust. And finally, a laid-back intern representing Python.
Right, the intern.
Right. And common sense says the accountant or the auditor finishes first, obviously. But today we're looking at this bizarre scenario where the intern they finish the job 5 times faster than the auditor. So our mission for you, listening right now, is to explore how these three languages handle the exact same complex math problems.
Yeah, and to really uncover why that accepted wisdom about which language is the quote-unquote fastest, why it just completely unravels depending on how an algorithm is actually structured.
Exactly. So what exactly are we looking at today? Where is this coming from?
So we're pulling the data for this exploration from a really phenomenal presentation. It's by a developer known as Lux036, and it's called the Combinatorial Generation Showdown.
Great title.
It is, yeah. And what they did was they built 3 sibling software projects.
Yeah.
So there's agents for Rust, agents Scipio for C++, and agents for Python.
Got it.
And they ran all of this on a massive 20-core Intel Core i9 processor. So, they're completely removing any hardware bottlenecks.
Yeah.
This is just a pure test of language architecture.
Okay, so to truly appreciate how the intern beat the auditor here, I think we first have to look at the obstacle course they're running. Because we aren't just asking these languages to handle web traffic or crunch random numbers.
No, why would not?
We're talking about combinatorial generation. And in the presentation, the author lists out this just incredibly dense lineup of tests. Things like EMK combinations using the Ehrlich 1973 revolving door method,
Right.
SJT adjacent swaps for permutations, Ehrlich star transpositions, binary reflected gray codes or BRGC, and set partitions using restricted growth strings.
Yeah, I can practically see your eyes glazing over already. It is quite a mouthful.
It really is. For anyone who, doesn't spend their weekends reading math papers from the 1970s, let's just pick 2 of those and visualize what the computer is actually being forced to do. So what is a binary reflected gray code?
Right, so think of a binary reflected gray code or BRGC, kind of like changing the dials on a combination lock.
Right.
But you have these strict rules. You have a sequence of binary numbers, so just zeros and ones, and you need to generate every possible combination. But the rule is you can only flip one single bit at a time to get to the next combination.
So you can't just spin all the dials at once.
Exactly. You can't change 2 dials at once. And when you try to generate, millions of these combinations, it requires this highly recursive logic. The computer has to dive down into a subproblem, flip a bit, dive deeper, flip another, and then constantly bubble those answers back up to the surface.
Wow. Okay. And what about the EMK combinations, the Ehrlich revolving door one?
So it's a similar concept, but with different rules. Instead of flipping a bit, you're swapping elements. Imagine a literal revolving door where every time the door spins, one specific item leaves the room and one specific item enters.
So every new combination is just one swap away from the last one.
Exactly. Each one differs by exactly one swap. So it's just very intricate, deeply nested mathematical work.
And here is the detail that completely hooked me on this source material, right? These 3 projects, they aren't just attempting the same general tasks. They are producing bit-for-bit identical output.
Yes.
It's like asking 3 different chefs in completely different kitchens using totally different tools to bake the exact same complex pastry. And all 3 produce millions of these identical pastries without a single crumb out of place.
Yeah. And enforcing that strict verification, it acts as this massive quality control check. In fact, the source notes that this cross-language checking actually caught a bug in the old Rust implementation of the EMK algorithm.
Wait, over a tiny mathematical swap, right?
Yeah, a single reverse instruction. So the Rust code was supposed to output a swap pair as I plus 1I, but it was actually spitting out I plus 1.
Oh, wow.
And in combinatorial math, if you mess up one microscopic swap, the entire sequence just completely breaks.
Yeah.
But because the developer was directly comparing the Rust output to Python and C++ outputs, they spotted the discrepancy immediately and fixed it.
That is wild, and it really proves the value of cross-language checking. But I mean, if the outputs are identical, if every single chef is producing the exact same pastry down to the atomic level, the only variable left is the clock.
Right, the speed.
Which brings us to the overall scorecard. So C++ wins the raw speed test. It takes first place in 7 out of the 12 benchmarks, which tracks, right? C++ is the veteran accountant here. Like in the EMK combinations test, I think it was choosing 5 items out of 16 C++, just absolutely dominated, finished in 1.27 milliseconds.
Yeah, C++ is exceptionally fast at executing raw, compiled instructions.
But then I look at the rest of this data, and this is where the Python Victory Lap comes in. Because Python beat C++ and Rust in 3 out of the 12 tests.
Yeah, and the data for the binary reflected gray code benchmark is particularly striking.
Oh, yeah.
For generating the sequence for 12 items, Python completed the entire run in just 2.64 milliseconds. C++, took a bit longer at 3.87 milliseconds, but Rust dragged way behind at 12.85 milliseconds.
I mean, Python didn't just beat Rust there. It completely annihilated it. It was roughly 5 times faster.
It was. And the gap actually widens with the set partitions benchmark. So generating those restricted growth strings for 11 items, Python finished in 150 milliseconds.
And Rust?
Rust took a massive 512 milliseconds.
Wow.
Yeah, over half a second compared to Python's fraction of a second.
Okay, so let's pause here because this is where the conventional wisdom just completely breaks down. Python is an interpreted language.
Yeah.
It's generally understood to be, slower because it's reading instructions on the fly, whereas Rust and C++ compiled down to bare metal machine code.
Right.
So how does the intern outpace the auditor so drastically here?
Well, it points to a pretty profound difference in how these languages handle deeply recursive tasks internally. Specifically, it's about how they implement generators.
Okay, break that down for us.
Sure. So a generator doesn't just compute an entire massive list of millions of answers and dump them into your computer's memory all at once. It computes one single answer, hands it to you, pauses its own execution, and then waits for you to ask for the next one. It yields a value.
It's kind of like a PE teacher handing out tennis balls one at a time from a basket rather than just dumping the whole bucket on the gym floor.
Yes, exactly. But remember, these math problems are highly recursive. So you don't just have one PE teacher. You have a chain of them stretching way down a long hallway. A generator function is calling a subgenerator, which calls another subgenerator deep down the line.
Right.
So the absolute critical bottleneck becomes how efficiently the language can pass a single tennis ball from the very end of that hallway all the way back up to you at the front.
And Python has a special trick for this passing of the ball, doesn't it?
It does. Python uses a command called yield from, and C++ has an equivalent concept typically implemented with coyield. When a Python generator hits a subgenerator, it essentially opens a direct, unobstructed pipe from that subgenerator straight back to the end user.
Oh, I see. So Python is acting like a smart manager. The manager just hands a clipboard of tasks to an assistant and completely steps out of the way. Like whatever the assistant gives you, just pass it straight through to the client. It delegates the whole thing in one smooth motion.
Exactly. That direct pipe is incredibly efficient. Now, contrast that with Rust's architecture for this specific task. Rust is relying on an engine called GeneAwaiter.
Okay.
And the thing is, GeneAwaiter cannot directly delegate in that same seamless way. It lacks that magical yield from pipe. Instead, it has to manually iterate through every single child value using a standard for loop.
So Rust becomes the micromanager here.
Totally.
It insists on individually approving every single piece of paperwork down a massive chain of command. Like, did you finish this one? Okay, hand it to me now. I'll hand up. Next one.
Yeah, and in computer science terms, that micromanagement means massive memory and processing overhead. First of all, this manual looping often forces a heap allocation for every recursive level.
Okay, let's ground that memory terminology real quick for the listeners.
Yeah.
Putting memory on the stack is like tossing a file on top of a neat pile on your desk, right? It's instant, organized, fast. But putting memory on the heap is like driving into a crowded parking lot and searching for a free spot. It takes vastly more time.
That is a perfect distinction, yeah. So Rust is basically constantly driving around that parking lot.
Wow, okay.
And second, GenoWaiter operates under the hood as an async state machine. So for every single microscopic step, every single yield up the chain, Rust has to pause and update this complex, heavy state machine just to remember exactly where it left off.
Okay, wait, let me push back on this a little bit because Rust is a compiled language, right? Backed by the LLVM compiler infrastructure, which is legendary for optimizing code.
Oh, absolutely.
So even if you write a manual for loop, shouldn't the compiler look at that, realize it's super inefficient, and just optimize that loop away into nothing? I mean, we're still talking about bare metal code versus interpreted Python bytecode. Why can't the compiler just fix it?
You'd really think it would, but you are hitting the fundamental wall of async state machines here. LLVM is incredible at optimizing standard synchronous code, but an async state machine wrapped inside a manual generator loop, it basically creates this opaque barrier.
An opaque barrier.
Yeah. The compiler looks at all these nested GenoWaiter calls and essentially gets confused by the complexity of the state transitions. It can't see through the nested layers to flatten them out, so it conservatively leaves all the heavy machinery in place. Meanwhile, Python's native yield despite running on an interpreter, is hard-coded in C underneath to do one very specific job flawlessly. That's delegation.
Wow. So it really is the difference between an intern who just rubber stamps everything instantly versus an auditor who refuses to skip a single bureaucratic check, even when it's bringing the whole company to a crawl.
Exactly. Which is why I think we really need to clarify where Rust actually shines in this showdown.
Fair point.
Because it isn't a failure of the language itself, it's a structural mismatch. When the mathematical algorithms were iterative, meaning they happen in a single flat loop without all that deep nested recursion, Rust matched C++ almost identically.
Like the Ehrlich star transposition benchmark.
Right, exactly that one, generating permutations using a single level loop. Rust finished that task in 8.84 milliseconds, and C++ took 8.87 milliseconds. I mean, it's a dead heat.
Okay.
The rule of thumb the presentation lays out is very clear. Rust is blazingly fast, just like C++ Ray, right up until it hits deeply nested recursion with generators. One level is totally fine, but deeply nested calls, the state machine overhead just crushes the performance.
Okay, so if Rust's biggest enemy here is its own micromanaging state machine, what happens if we fundamentally change the paperwork itself?
Yeah.
Because developers are constantly rewriting algorithms to be smarter. If you optimize the underlying math, does that relieve the bottleneck, or does the language's mechanics still choke it out?
Well, that is the exact question the developers of these projects tested next. They actually created a suite of new algorithms to pit against the old algorithms.
Oh, I love that.
Yeah, they took the mathematical logic and tightened its structure just to see how C++, Python, and Rust would react to the exact same upgrade.
And to be clear for you listening, the actual output, the millions of generated combinations that remained identical, we're just changing how the computer navigates the maze. So what were the specific tweaks?
So let's break down two major ones. First, the EMK algorithm generated those combinations. The old version utilized a two-helper structure. What that meant was that at every single level of recursion, as it dove deeper, the computer had to stop and check a parity condition. It basically asked, am I on an even step or an odd step?
Got it. So you have a toll booth at every single intersection on the descent.
Perfect analogy. The new version upgraded to a four-helper structure. It pre-specialized the functions right at the entry point. So it essentially said, hey, this entire path is only for evens, and this entire path over here is only for odds, completely eliminating those toll booths at the lower levels.
You just get on the highway and drive.
Exactly.
Did they do something similar for the set partitions?
They did, yeah. The second major tweak involved guards. And a guard is just an if statement checking a condition before running a block of code. So the old set partitions algorithm wrapped the entire function body in one very broad guard. But the new version used tight guards placed precisely at each recursive call point.
Okay, let me guess the impact of that. With a broad guard, the program dives all the way down into a subgenerator, opens up the kitchen, only to realize it doesn't have any ingredients, so it just returns empty-handed. It's wasting cycles, setting up operations that yield absolutely nothing.
You've got it exactly. The tight guards check the inventory before ever opening the kitchen door, so they entirely avoid wasteful, empty subgenerator calls. It is a really brilliant, undeniable mathematical improvement.
All right, so the math is undeniably smarter. How do the languages actually reward this better math?
Well, the disparity of the rewards is pretty staggering.
Yeah.
C++ took these tweaks and absolutely flew. For the EMK combinations, the new four-helper structure gave C++ a massive 2.02x speedup. The execution time literally halved.
Wow. Why did C++ respond so aggressively to that toll booth being removed?
It's because of the compiler mechanics. When you remove that parity check at every single level, you stop confusing the CPU's branch predictor, which is the part of the chip trying to guess which way an if statement will go.
Right.
Furthermore, the MSVC compiler for C++ performs incredibly aggressive coroutine elision. Basically, it looks at the simplified, toll-free recursive chain, realizes it doesn't need to allocate memory on the slow heat parking lot at all, and just squashes the whole state machine directly onto the fast stack. Or it just inlines the code entirely. C++ translates the smarter math directly into optimized machine code.
Man, it just directly rewards the developer's hard work. What about Python?
Python was very consistent. It saw a reliable speedup of roughly 30% across the board. The smarter math just meant the interpreter had fewer bytecode instructions to read and execute, which gave it a solid, measurable boost.
Okay, so the C++ accountant works twice as fast. The Python intern works 30% faster. What happens to the Rust auditor?
This is tough. For the deeply recursive EMK tweaks, going from the 2-helper to the 4-helper highway Rust, saw a speedup of roughly 1.02x to 1.06x.
What? That is basically statistical noise. It's practically a 0% improvement.
Yeah.
You write a brilliant mathematical optimization and Rust basically just ignores it.
It is a harsh truth. And honestly, it reveals the profound takeaway of this entire showdown. Rust's genoator overhead. The constant searching for a parking spot on the heap, the updating of the async state machine, it is so dominant that algorithmic reorganization barely registers.
Wow.
The complex math isn't the bottleneck for Rust here. The paperwork is the bottleneck.
That is fascinating. You could invent the greatest algorithm in human history, but because the language itself is struggling to pass the forms up the chain of command, the brilliance just doesn't matter.
Exactly. In fact, the source presentation concludes something highly counterintuitive based on this. For Rust, in this specific recursive scenario, it is actually better to keep the old, simpler 2-helper code.
Wait, you are saying developers should intentionally keep the less efficient math algorithm?
Yes, because the new 4-helper code is a lot more verbose, it requires more functions, and increases the code surface area, which obviously increases the cognitive load for anyone reading it. If the complex math doesn't give you a speed boost anyway, because you are hitting the language's optimization ceiling, why introduce more complex code? Just keep it simple.
That is crazy. Better code isn't always faster code. It depends entirely on how the compiler and the internal language mechanics digest it. So, bringing this all together, how do we make sense of this? 3 languages, identical output, completely shattered expectations. What is the final verdict for someone trying to actually choose a tool?
Well, the source outlines some very practical takeaways. If your absolute priority is raw, blistering speed, and you are willing to manage a bit more build complexity, you choose C+++.
Makes sense.
The compiler optimizations for coroutines are simply unmatched, and that allows it to win the majority of the tests outright.
The veteran accountant wins the main event.
Right. However, if you are working heavily with deeply recursive generation and you value code readability, Python is surprisingly competitive. And this perfectly illustrates what the author calls the ponytail principle.
The ponytail principle. Let's spend a second on that because it feels central to why Python did so well here.
Yeah, so the ponytail principle suggests that sometimes the most unassuming, straightforward approach is practically superior to a highly engineered one. It's the idea that simple, readable code like Python's native yield from is often fast enough.
Yeah.
And in bizarre edge cases involving deep recursion, it might actually outpace the heavily engineered solution because it isn't fighting its own underlying architecture.
I can absolutely see that applying to real-world engineering.
Yeah.
Like, you could have a developer spend 3 weeks trying to write incredibly complex, safe, async Rust code to squeeze out performance, when a 10-line Python script using a simple yield from command would have run 3 times faster and taken 5 minutes to write.
That is exactly the pitfall the principle warns against.
So where does that leave Rust in the final verdict?
Well, you choose Rust when you absolutely need its legendary memory safety guarantees, like when crashing is simply not an option, and when your algorithms are primarily iterative, single-level loops. In those tasks, Rust is neck and neck with C++C. But if your problem shape is deeply recursive, You just have to accept that Rust's current generator implementation comes with an immovable speed limit.
You know, we spend so much time in the software industry debating which programming language is definitively the best or inherently the fastest. We treat speed like it's this fixed stat on a video game character.
Oh, totally. We do.
We assume C++ is always a 10 out of 10 on speed, and Python is always a 4.
It's a very comforting hierarchy, but it's an illusion. Performance is highly contextual.
And this combinatorial showdown just completely dismantles that hierarchy. It proves that performance isn't a fixed trait of the tool. Performance is born from the microscopic friction between the mathematical structure of the problem you are solving and the invisible compiling mechanics of the language you're using to solve it.
Absolutely.
If a tiny structural shift in an algorithm like removing a parity toll booth can double the speed in C++ sort, give Python a solid 30% boost, but do absolute nothing for Rust because it's too busy managing its own paperwork, it really forces us to reconsider how we approach engineering.
You have to know the shape of your maze before you choose your runner.
I love that. And it leaves you with a question to mull over the next time you boot up your editor or debate a tech stack with your team. Are we actually evaluating our programming tools based on their true underlying mechanical capabilities? Or are we just judging them based on the shape of the problems we usually feed them? Because it turns out, if you change the recipe, the intern might just bake the pastry faster than the master chef.